Hello everyone, this is Dr. E, and for today we're going to be working on triangle inequalities and its theorems that will help us answer in problems involving triangles similar to this one. Hello everyone, this is Dr. E, and for today we're going to be working on triangle inequalities and theorems associated with this type of triangle. Problems in geometry can sometimes be a little bit challenging, especially if it's testing our critical and analytical thinking skill, and this is what we're going to be working on in our lesson today. So first, let's learn the comparison property of inequalities in a triangle. So in a triangle, if A is equal to B plus C, and if we're talking about A, B, and C, we're talking about the side lengths of the triangle, and C is greater than 0, then we know that A is greater than B, which can be a little bit abstract for most of you. So if you remember our lesson on exterior angle of a triangle, it just tells you that the measurement of the exterior angle, which is 1 right here, is equal to the measurement of angle 2 plus the measurement of angle 3. So that's basically the measurement of angle 1. That's why we're able to produce this comparison property of inequality, wherein A will always be greater than B, knowing that we have a triangle similar to this one. And some corollaries or theorems associated with the main theorem that I have just shown you. We have the corollary to the triangle exterior angle theorem, which means if the measure of an exterior angle of a triangle is greater than the measure of either of its remote interior angle, then we'll have a triangle similar to what we are seeing in this statement. So if angle 1 is the exterior angle, which is this angle right here, we know that the measurement of this angle will be greater than the measurement of 3, and the measurement of this angle is greater than the measurement of this angle 2. So that's basically this particular corollary for the triangle exterior angle theorem, which we're going to be using so that we can show that the measurement of angle 2 is greater than the measurement of angle 3. And what are those angles? Measurement of 2 is somewhere here in this diagram, and the measurement of 3 is somewhere here in this diagram. Now, we are seeing so many labels and points in this figure, but we are not seeing any measurements that can determine or verify if this statement is true. So to be able to do that, we have some clues that we can work with. And the clues are, we are seeing an isosceles triangle right here because we know that these two sides are congruent. And when those two sides are congruent, we also know that these two corners right here, or angles, are also congruent, and that is the isosceles angle theorem. So if we are seeing this triangle, just to make it a little bit more visual, and this is how I always work with problems like this in geometry. I often draw my figure, even though my figure is a little bit crooked, but here I am seeing what I need to show, and what I need to show is that this angle, angle 3, or angle 2, not angle 3, is greater than this angle, which is angle 2. And I know that these two sides are congruent, and when these two sides are congruent, these two angles are also congruent. And this will help me prove that measurement of angle 2 is greater than the measurement of angle 3. This is 3, not 2. And this is 2. So let's make it a little bit clearer using a better writing. So how are we going to show that? We are seeing that if we extend this side, we are seeing an exterior angle right here, and we know that this exterior angle will always be bigger than the measurement of angle 3. So if this measurement is bigger than the measurement of angle 3, and if this measurement is congruent to angle 2, that proves that the measurement of angle 2 is indeed greater than the measurement of angle 3 using those theorems, the exterior angle theorem and the isosceles angle theorem. So those are the two theorems, isosceles angle theorem and the corollary of the exterior angle theorem. To prove that the measurement of angle 2 is indeed bigger than the measurement of angle 3. So this is how your thought process should go. So you are seeing that we have to show that angle 2 is greater than angle 3. We know that this is an isosceles triangle right here, DBC. And since angle 1 is congruent to angle 2, using the isosceles triangle theorem, we can now show that if we extend this triangle side, we are seeing that we can use the exterior angle of ABD to show that the measurement of angle 1, which is the exterior angle of this triangle associated to the measure of angle 3, is bigger than angle 3 using the corollary of the triangle exterior angle theorem. So from here, on this point, we can show that the measurement of angle 1 is greater than the measurement of angle 3, which happens to be congruent to angle 2 because of the isosceles triangle, that isosceles angle theorem. We can now show that the measurement of this angle, angle 2, is indeed greater than the measurement of this angle. So that is how we use our theorems in showing or proving problems similar to what we just had. And now we're working on the triangle inequality theorem, which states that if two sides of a triangle are not congruent, then the angle opposite the longer side is greater than the angle opposite the shorter side. So you are seeing in our diagram a statement wherein it shows that xz, or line segment xz, is greater than xy. So the longer side is xz than xy. So that means, in conclusion, the measurement of angle y is also greater than the measurement of angle z, which are the opposite angles of the longer side and the shorter side of this triangle. And to make it a little bit more visual, if we have a triangle similar to this one, this is a triangle, this is a triangle, and this is our triangle. And we know that 1, 2, 3 sides. The longest side of this triangle is this side right here. So if this is the longest side is side 3. The biggest angle will be this angle because of this triangle inequality theorem. And the shortest side, which is side 1, its opposite side right here would be the smallest angle among the three angles that we are seeing. So that's basically what this theorem is telling us, which will help us in answering problems in a little while. And so if we have the triangle inequality theorem, we also have the converse of this theorem, which just shows that if the measurement of angle A is greater than the measurement of angle B, then side BC, which is the opposite side of angle A, is longer than the opposite side of angle B, which is angle B, which is side AC. So in these statements, if two angles of a triangle are not congruent, then the side opposite the greater angle is longer than the side opposite the lesser angle. So that is the converse of the theorem that we have just shown a while ago, which we can use to solve this problem. So in this problem, a town park is triangular. So we are seeing a triangle in this park, and a landscape artist wants to place a bench at the corner with the largest angle. Now the question here is, which corner has the largest angle. And to be able to do that, all we need to do is to see the measurement of the streets around this park. And we are seeing Hollingsworth Road, MLK Boulevard, and Valley Road. And we are seeing that this road is 175 yards, 105 yards, and 120 yards. So obviously, Hollingworth Road has the longest street in this particular area. So that means Hollingsworth Road has the longest side, and opposite its longest side, using our theorem, will give us the biggest angle among the three corners that we are seeing in this park. So to answer this question, which two streets from the corner with the largest angle are we looking at? And that would be the MLK Boulevard and the Valley Road, or Valley Road, that contains the largest corner in this park. So this is how we use that theorem in identifying this particular corner that we are trying to find. And the last theorem that we're going to be using is the Triangle Inequality Theorem for the sum of lengths of side, which tells you that the sum of the lengths of any two sides of a triangle is always greater than the length of the third side, which basically tells you that if you add two sides of the triangle, the sum of that two sides will always be greater than any of the third sides. So in this case, if we add xy and yz, its length will always be greater than side xz. And that is always going to be the case if we're going to choose two sides and add it up, and it will always be longer than the third side. So that is this theorem, which we're going to be using to identify which between these two triangles are valid form of a triangle. And to be able to do that, we know that in the theorem a while ago, the sum of the two sides will always be greater than the third side. So we are going to check it for the first triangle. And how are we going to check it? So for the first triangle, we have 3 feet by 7 feet by 8 feet. So this is our triangle. And to check if this is a valid triangle, we'll add 3 plus 7 and see if it's greater than 8. We will add 7 plus 8 and see if it's greater than 3. And we're going to add 8 plus 3, which should be greater than 7. So if all of them are greater than these inequality, then we know that we have a valid triangle. And to check that, if we add 3 plus 7, 7 plus 3 is 10, and 10 is indeed greater than 8. And if we add 7 plus 8, 7 plus 8 is 15, which is also greater than 3. And 8 plus 3 is 11, so it's also greater than 7. So all three inequalities are true. That means this triangle is a valid triangle, because when we pick those two sides, we're seeing that all of them are indeed greater than the third side. So this is how we use that theorem. So for the next one, if we are going to use the same technique, we'll have 5 feet, 10 feet, 15 feet. So if we add 5 plus 10, is it going to be greater than 15? If it's 10 plus 15, is it greater than 5? If it's 15 plus 5, is it greater than 10? And by using the first option that we have here, 5 plus 10 is equal to 15. And this is already not greater than 15 because this is an equation, or they are the same. So that means from this first pick, we already know that the theorem is not holding true. So that means this particular triangle does not exist, since the sum of 5 and 10 is not greater than 15, but equal to 15. So it contradicts the theorem that we just had. So this is how we use the Triangle Inequality Theorem. So your Numberbender challenge for the day is to see if the two sides of a triangle are 5 feet and 8 feet long, what do you think is the range of the possible lengths of the third side? So you're going to give me the range of lengths of the third side of this triangle for this triangle to exist, because it cannot be 298 feet because we know it's too long and it's not going to fit to the two sides of 5 and 8 feet long. So see if you can figure out a way on how to give me the range of lengths in feet for the third triangle so we can complete, third side, so we can complete this triangle. And this is our lesson for today on triangles. So we have learned new theorems that we can use to further our skill in critical thinking and analytical thinking and geometry problems similar to what we have shown today. So again, it's a challenge, but with practice, it will help you gain the confidence that you need to be able to do more or answer more problems in geometry similar to what we did today. This is Dr. E, and see you again next time.